Welcome to the second of the AMS Colloquium lecture series. I would just like to point out that you should not sit in the back of the auditorium because it's a fire hazard, so please try to find any available seats as soon as you can. So our speaker today, Terence Tao from UCLA, needs no introduction. He's famous for his many great contributions to mathematics across many areas, including analysis, probability, combinatorics, number theory, and many others. Today, he will talk to us about translational tilings of Euclidean space. Please join me in welcoming Terry.
Thank you very much. Yeah, so this talk is not related to the other two talks. In particular, well, I have one AI-generated image in this talk, but other than that, there's no really computers or machines involved here. So this is a topic which I chose because it's a very accessible topic, and it turns out to also be a topic that has actually got a lot of popular attention recently, as I'll tell you. So it's a question of, it's one of the, oh, it's already a type on the first slide. That's not a good sign. But yeah, it's a very basic concept in mathematics, just tiling space, and something that's very accessible, but for which many of the basic questions are only recently answered, and still are open questions in the subject. So let me start with some basic notation. So we're going to tile space, and space, by space, I mean an abelian group. It could either be Euclidean space, R2, R3, or maybe a discrete lattice like Z2 or Z3, or we can tile a finite group. And by a translational tiling, or tiling for short, what that means is that you take a subset of your group F, and you will translate it by various translates, and if you can translate in such a way that you can partition your space into translates of your single tile, maybe up to measure zero sets if you're tiling Euclidean space. We call that a tiling. The set of translates we normally call A, and that's the tiling set. And if the translates of F by A partition G, we say that A direct sum F equals G. And so we're basically interested in solving this equation for which A and F is true that A plus F equals G. Seems like a very simple, innocuous equation. Many tilings are periodic, so I'll take the time to actually define that. Inside an abelian group G, you define a lattice, lambda, to be a subgroup whose quotient is compact. So for example, in Z2, if you take 2z squared, the set of all points in Z2 where the coordinates are even, that is a lattice in Z2. Z2 is itself a lattice in R2, because the quotient of R2 by Z2 is a torus, and that's compact. And so if your tiling set is invariant under shifting by a lattice, then that's a periodic tiling. Okay. This is tiling by one tile. People also consider tilings by multiple tiles. So you may have J tiles, F1 to Fj, and maybe the individual tiles cannot tile the space by themselves, but some combination of the tiles together by translation do tile. And so you can generalize the notion of tiling without much difficulty. Sometimes I'll refer to monotilings as tilings involving only one tile. In this talk, we will mostly consider translational tilings. So your tile you're allowed to shift, just add and subtract by shifts, but you're not allowed to rotate. But people do also consider tilings, say, of R2, where you can translate and rotate. These are called monohedral tilings, and sometimes you also allow reflections as well as rotations. So that's also very interesting, but I'll focus on translational tilings, which have additional structure. So I think I have some examples of tilings. Okay, so Escher in particular has many, many examples of tilings. This is a periodic monotiling of R2 by a Pegasus. So one of these Pegasi you just call F, and then all the other Pegasi are translates of F. They're different colors, but never mind the colors. And this is the translation. This tiling is periodic because the set of shifts is actually basically just Z2 up to scaling. So this is a periodic monotiling. This is a periodic monotiling, a periodic tiling with two sets, a cat and a dog. So the cat and dog do not tile space separately, but together they do. And the set of shifts, I think there's twice as many cats as dogs. So the set of shifts are a bit different, but they're both periodic with the same lattice. So this is also considered a periodic tiling. Okay. Here's an example of a non-periodic tiling. So if you take a unit square, F, you can tile R2 periodically with F. You just shift your unit square by the standard lattice C2, and that gives you your standard graph paper tiling of R2. But this tiling is not rigid. You can take your standard tiling and you can take one row of your tiling, as I've done here, and just shift it by a little bit. And now it is not periodic. The way we've defined it is not periodic anymore. It's what you might call weakly periodic. It's still periodic in one direction. This new tiling is, the tiling set is still invariant with respect to horizontal shifts, but I have broken the vertical shift invariance. And so the set of shifts is no longer a lattice. It is just an infinite subgroup. So by my notation, this is not a periodic tiling. In different literatures, this might still be called periodic or one periodic. The notation is not completely uniform in the literature, but for this talk, this is what I would consider this a non-periodic tiling. So the unit square has both periodic and non-periodic tilings. Okay, so what I like about this particular problem is you can divide mathematics broadly into sort of structured mathematics where there's lots of symmetries, lots of structure, and like it's very algebraic and very rigid. And so like tools from algebra become very useful. And then there's sort of the more analysis probability side of mathematics where things are very random and there are very few constraints and things are very non-rigid. And translational tilings are somehow in between. They have a lot of algebraic structure, but not as much structure as you'd see in like a group or a representation. They're not so rigid that you can hope for a full classification, but they do have unexpected structure. I mean, this equation A plus F equals G has, well, you can do many things with it, and it is connected. It is very naturally connected to many areas of mathematics, and so there's many types of things you can do to analyze these tilings, particularly translational monotilings. There's lots of things you can do with that particular combination that you can't do with either monohedral tilings where you tile but with rotations, or with translational tilings with multiple tiles. So for example, one thing you can do is that you can start using Fourier analysis. The equation 1 plus F, A plus F equals G, that F tiles G by A, is equivalent to saying that if you take the indicator function of A and the indicator function of F, let's say you're in a discrete group so that I don't have to worry about measures and so forth, and you just convolve these, that's equal to 1. If you find out what convolution means, this is an equivalent form. So we're just solving a convolution equation, right? So given a tau F, what are the indicator functions of 1 sub A, such that 1 sub A convolve 1 sub F equals 1. And that's a very simple equation, and it's very tempting to take the Fourier transform of this equation. And now, if you know the Fourier analysis is the same as saying the Fourier transform of 1 sub A times the Fourier transform of 1 sub delta of 1 sub F is the Dirac delta function, or Kronecker delta, depending on whether you're a finite group or whatever. And that seems like an equation that you can start solving. You can try the same thing for more tiles, but the equation is no longer so algebraically easy to, not so tractable. So people do successfully use Fourier analysis to understand tilings, but it doesn't fully solve the problem. It reduces things to a deconvolution problem, but not all deconvolution problems are easy. This equation also has some symmetries. Okay, so there's some obvious symmetries. If you take, if F tiles space, then any transit of F also tiles space, and any reflection of F tiles space, and so forth. There's some sort of obvious algebraic symmetries, but there's some less obvious symmetries. Like if F tiles space with a certain tiling set A, then it turns out that the reflection of F also tiles space with the same translations, with the same set A. So that's unusual. Like what is obvious that if F tiles G by A, then minus F tiles G by minus A. But it also tiles F by plus A as well. So that's a cute symmetry. It's actually not, once you say it, it's actually not so difficult to verify. The key observation is a really elementary algebraic fact, which is that in any group, any abelian group, if A plus F and A prime plus F have the same sum, then there's also the same difference. A minus F prime is equal to A prime minus F. Right? That's just, you just rearrange the sum to a difference. And that's not, that plus a tiny extra argument gives you this reflection symmetry. There's also a less obvious dilation symmetry. If you have a tau F, which tau's space by some translates F, you can dilate F by a prime, P, and as long as the prime is actually, the order of the prime is co-prime to the order of the cardinality of the tile, if you have a finite tau, then the dilate also taus by the same space. I should have given an example. So there's no slide here, but if you take the set 0, 1 in the integers, so this 2-point set, 0, 1 tiles space using the lattice 2z. So if you take 0, 1, you shift it by 2, 2, 3, 4, 5, and so forth. That tiles the integers. So the integers, 0, 1 tiles the integers using 2z as your tiling set. If you dilate 0, 1 by 3, 3 is co-prime to 2. 0, 3 also tiles the integers by the same shift. If you take 0, 3 and you shift it by multiples of 2, if you think about it, that also tiles Z. And so that's a general phenomenon. There's a dilation symmetry, and this is a special property of translational monotilings. Most other tiling problems do not have this extra symmetry. The proof is really cute, but I'm not going to give it. I'll just say that the main ingredient is sometimes what's called the freshman's dream. That if you raise A plus B to the P, you're not supposed to distribute it. Usually it is not A to the P plus B to the P, okay? And if you do that as an undergraduate, because you're usually not in characteristic P, that is a bad thing to do. But in rings of characteristic P, this is actually a true identity, the Frobenius identity, and this is actually what's used. So you can write this dilation symmetry in convolution form, and you look at the convolution algebra mod P, and you use this identity, and a little bit of magic. It's a half-page argument, but I will skip it. If you're bored, you can try to prove it yourself. Okay, so there's some there's some algebraic structure. I mean, it's not sort of it's not a complete algebraic structure like a representation or something that you could start going to town with, but it lets you do non-trivial things with tilings. Tilings are also very closely related to dynamics. Given a tau, you can look at all the possible ways you can tau a space with a single tau, and that whole set of possible tilings is itself an interesting space. You can give it a natural topology, and usually it has the topology of a compact space. I mean, this equation A plus F equals G is in some sense a closed equation. And it's a transition invariant space. As I said, if F taus G by A, you can shift A, you can shift the entire tiling, and that gives you a new tiling. Sometimes it gives you the same tiling if your tiling is periodic. So this compact space is also a dynamical system. Your space acts on this space of tilings by translation, and like periodic tilings are precisely those are the periodic points of this dynamical system. So it becomes very natural to start using the language of topology of dynamical systems and ergodic theory and so forth to analyze these equations too. And there has been much. It's been a very fruitful connection. So I just want to say, so even though tiling is somehow a very elementary and it's one of the few areas of mathematics you can even explain to a non-mathematician without too much difficulty, it does connect to all kinds of other fields of mathematics. So what I like about these tilings is that on the one hand, they do have a certain amount of structure, and so like they're not just sort of completely arbitrary equations, these tiling equations, but not quite enough to make them so rigid that they're boring, or that they're algebraic, completely algebraic. These are not the same thing, of course, but that they still have kind of a lot of richness, and in fact, the kind of richness that they become kind of undecidable and sort of unspecified, especially in higher dimensions. Of course, this is even true in algebra. Like things like the word problem for groups and so forth. Become undecidable eventually. And there's a lot of surprises. There's a lot of conjectures. So low-dimensional tilings. So 1- and 2-dimensional tilings in particular, we understand pretty well. And it is very natural to extrapolate from low-dimensional intuition what happens in high dimensions. But what we are beginning to learn in tiling is that high-dimensional tiling is a very different beast from low-dimensional tiling. Many conjectures that are very natural and can even be proven in low dimensions fail in high dimensions. And we now have many examples of that, and I'll give you one of them in this talk. Yeah, so somehow the thing is that the single equation, 1a convolve 1f equals 1, it's a very interesting, it has a very interesting solution space. Like it's not as rigid as, say, an algebraic variety, but it's not like a random set either. It's something in between. And that I quite like, this sort of intermediate structured type of problem. Okay, so what are the type of questions, and there's many questions you can ask about tiling. Okay, so I'll focus on sort of two basic questions, and I'll phrase them first in informal form. So informally, if I give you a set F, so the first basic question is, can a tau F G at all? Okay, so some sets tau and some sets don't. For example, the set 0, 1, as I said, in the integers, does tau the integers. You can shift 0, 1, and it covers the integers. But many sets don't tau. I won't explain why, but 0, 1, 3, for example, does not tau the integers. In fact, because 0, 1, 3, it omits 2, and there's no way to fit 2. There's no other translate of 0, 1, 3 that can cover that hole. So some sets tau, some sets don't. Is there an easy test? Is it even a decidable question? Can you get a computer algorithm to test whether F tau is G? And then if it is a tile, what can you say about what other possible tiling, what is the space of possible tiles? Is there some structure to those? So these are basic questions. So here are some more precise versions of this conjecture, of this assertion, of these problems. So the first is what I would call logical decidability. If I give you a set, a finite set F, and ask, can it tau, is there some way to shift it back and forth so that it taus the whole space? Is this even a decidable statement? Right? Is it even provable or disprovable that either you tau or you don't tau, right? In whatever your favorite model of logic is, let's say ZFC set theory. So this is a question of logical decidability. Is things provable or not provable? Closely related to that is the notion of algorithmic decidability. Is there a computer program which, if you feed in a tile, it will run, and in finite time, the program will halt, and it will either say, yes, this tile taus space, or no, it doesn't. These are very basic questions. Right? You would think that the theory of tiling would be kind of embarrassing if you can't answer these questions. And then there's another question more about the structure of tiling. That let's say you're in a discrete space. If you have a tau F, and you know that there's some tiling of space which is not periodic, so we know that sometimes tiles are not periodic, tilings are not periodic. So I gave you this example of the unit square tiling, and you shift it a little bit, and you have this tiling that is not completely periodic. But the unit square tiles non-periodically, but it also can tile the space periodically as well. And the question is that a universal phenomenon? So if it's possible to tile space at all, can you modify the tiling, can you fix the tiling to actually be periodic? So so does the existence of a tiling force the existence of a periodic tiling? Another way of saying that is that you can call a tile aperiodic if the only way that you can tile space by this tile is using non-periodic tiling sets. And the question, and there's a conjecture, quite an old conjecture actually, called the periodic tiling conjecture, is that there are no aperiodic tilings. That every tile that tiles space at all must be able to tile periodically. It can also tile non-periodically, but it must tile periodically as well. So these are three basic questions. And one reason why I list them all together is that they are logically related. So for example, the first two are related. If you know logical decidability, if statements, if the tiling problem is never logically undecidable, so it's either provable or disprovable, then it is also algorithmically decidable. So this has nothing to do with tiling. This is a very general implication in complexity theory. So if you know that every tiling question, whether F tau G is either provable or disprovable, that gives you an algorithm to test whether. Okay, there's a caveat. You have to assume ZFC is consistent. Okay, but we're going to do that. That gives you an algorithm to test whether a certain tile is tile space or not, because basically you just get your computer to search through all possible proofs or disproofs in ZFC that you tile or you don't tile. And there's only countably many possible proofs and disproofs, and you just go search. This is not an algorithm you'd ever implement. This is a horrible algorithm for performance-wise, but it is an algorithm that will terminate in finite time if you have logical decidability. And so this tells you that anything which is logically decidable is also algorithmically decidable, assuming your theory is consistent. Just a side note, also gives you the shortest, probably the shortest proof of the Gödel incompleteness theorem. Okay, so Gödel incompleteness theorem says that there exists systems that are logically undecidable, and that's a corollary of the fact that there exist algorithms that are algorithmically undecidable by this argument. And the undecidability, say, of Turing machines is quite easy. It's an easy diagonal argument. Okay. So that's one connection. The converse is not quite so clear, actually, but still, when you have one, you usually have the other. Another basic observation made in the 60s by Hao Wang, is that this periodic tiling conjecture implies logical decidability and hence also algorithmic decidability. So one reason why you want to know that tilings, that there are no aperiodic tiles, is because it makes the problems decidable. For why? Okay, so you have a set F and you want to know whether it tiles or not. So there are three cases. Okay, so if it tiles periodically, then you can easily make that into a proof of tiling. Okay, because a periodic tiling can be described using just a finite amount of data, and you can verify that a periodic tiling tiles using a finite program, and you can make a finite proof that it tiles. So it's not difficult to turn a periodic tiling into a finite proof that tilings exist. Conversely, if a set F doesn't tile all the space, then there's a very general theorem in logic called the compactness theorem that says that already there must be some finite subset of your space that cannot be tiled, maybe with some stuff left over, maybe with some excess by your space. If you want to prove that you can't tile, it suffices to find a finite set that already can't be tiled. And that you can just and exhibit. Like you just write down a finite set, and there's a proof just by finite case check that there's no way to cover this space by disjoint translates of F. So if you don't tile at all, you can prove it in finite time, and if it tiles periodically, you can prove it in finite time. And so the third case is the aperiodic case, where you do tile, but only aperiodically. And there's no obvious way to either prove or disprove in finite time that you tile. But the periodic tiling conjecture says that the third case doesn't exist, that there are no aperiodic tiles, and so you only are in the decidable cases. So this is one of the historical motivations for studying this conjecture. There was a whole string of positive results, so I'll just give you some. If you want to, so the periodic tiling conjecture, if you want to only tile a finite group, then it's obvious because trivially everything is periodic in a finite group because the trivial group is a lattice. So that's sort of the zero-dimensional case. That's the trivial case. We also kind of understand the one-dimensional case. If you tile the integers or the reals, or the integers cross a finite group, so all these sets that are sort of asymptotically one-dimensional, there are easy arguments. So for the integers, for example, there's an easy argument based on the pigeonhole principle in fact every tiling is periodic in the integers. And again, if you're bored, you can try to work out in your head why that's the case. In fact, that's even true even if you have multiple tiles. What's less obvious is in 2 dimensions, at least in the discrete case, Z2. The conjecture is also true. That's much more recent. That was done in 2020, using the dynamical systems approach that I mentioned previously. Rachel Greenfield and I, we have also made an alternate proof after seeing that paper. R2 is an interesting question. Actually, there's some partial progress right now, but actually, we don't know whether it's true in R2 or not yet. In higher dimensions, there's another partial result of Mario Zegedi. If you're in ZD and your tile has a prime order, or it's very small, as order at most 5, then it's true. So there's some partial progress there. But there are lots. But the conjecture does break down in many cases. So you can, for example. The conjecture talked about only monotilings. If you have many tiles, it turns out the conjecture fails, and this was known for quite some time. So there are sets of J tiles, so J bigger than 1, which tile space together, but maybe Z2 or R2 or whatever. But but the only ways that you can tile them are non-periodic tilings. So these are called aperiodic tile sets. And there's now many such tile sets known. And in fact, not only is the periodic tiling breaks down, but also decidability breaks down. So there are finite sets of tiles where it is not decidable. You cannot prove or disprove whether this a finite set of tiles space or not, which is a remarkable result, actually. So you can find a finite number of tiles in Z2, just finite sets, completely concrete. You can even write them down in principle, for which we know it is not provable or disprovable, assuming Z2 is consistent. That you can that they tile or not, which is remarkable. These tilings, some of them are quite famous. So maybe until last year, maybe the most famous tiling, aperiodic tiling, was the Penrose tiling. So the Penrose tiling is, in our language, so it's normally phrased in terms of 2 diamonds, but you allow them to rotate in 5 different ways. But because we're not allowing rotations, I have to make 10 tiles. So if you take there's a green diamond, which is sort of long and narrow, and a blue diamond, which is fatter, and there's 5 different ways to rotate each of them. So that gives you 10 different tiles, and if you translate them back and forth, it is possible to cover all the space with these 10 tiles, but only in a non-periodic fashion. Okay, so that's the Penrose tiling. This tile is called the Sokoler-Taylor tile. This is a single tile where you can rotate it, rotate and reflect it, 12 different times. And it is possible to cover all the space by 12 different rotations and reflections of this tile. It's not a connected tile, but we don't enforce connectedness always. Again, the only way to tile space turns out to be aperiodic. And there's all these little funny ridges and bumps and so forth, and those are, they're what kind of force. This is a perturbation of the unit hexagon. Unit hexagon tiles periodically, but this sort of perturbed hexagon doesn't. But probably many of you have heard about this tile, the hat tile, which was only discovered last year. So that's this polygon, this non-convex polygon shaded in gray here. And this is a non-periodic monohedral monotile. So it's connected. In fact, it's even a topological disk. And there are, I think, 10 or so different rotations and reflections of this tile, which cover all the space. But the only way to tile all the space is, again, aperiodic. I think this is maybe the most successful mathematical outreach of a mathematical research result in the last, let's say, at least 5 years. It made social media. People, posted pictures of cutting out 3D printing bathroom tiles with a hat. It even made the Jimmy Kimmel show. It's a tile that only you need to rotate and reflect it, and then shortly afterwards, the same group of people produce a variant, which they call the spectre, and it's a very similar tile to the hat, except that you can tile space now without needing reflections. It's what they call a chiral monotile. There's, again, I think 12 rotations of this tile, which tile space, but not. And again, the only tilings are aperiodic. They do have kind of an almost periodic structure. They have this sort of self-similar kind of p-adic type of structure, but they're not actually periodic. So I've been working with Rachel Greenfield for quite a while on this, for a couple of years on this in this area, and we have a different approach. So we eventually sort of realized that the high-dimensional case was quite different from the low-dimensional case. And our results show that things are really pathological in high dimensions, that even though there's always positive results about tiling in low dimensions, it's not indicative of what happens in high dimensions. So in high dimensions, in sufficiently high dimensions, the periodic tiling conjecture fails. There are tiles in high dimensions for which the only tilings are non-periodic. And you can kind of make it almost two-dimensional. And in fact, the same thing is true even in Z2 cross a finite group. So even though periodic tiling is true in Z2, it's not true in virtual Z2. And also, most recently, we showed that the decidability is also false in high dimensions and also in virtual Z2. And there's a talk by Rachel this afternoon, actually, about that. So in sufficiently high dimensions, things are bad. What is sufficiently high? In principle, we could compute it, but the way our proof is structured, it's incredibly enormous. 2 to the 100 type dimension is the type of thing we have. Yeah, so it's still of interest, so we know periodic tiling and decidability is all true in, say, Z2. R2 is very interesting and very natural. Z3 is also open, so those are very natural. Yeah, but there are results on undecidability. If you impose more conditions on the tile, then sometimes there are positive results. Like if you have convex tiles and so forth, there are some partial results. There's a recent result of Greenfield and Kountzakis about connected tiles, which there was a talk yesterday actually about that. So I will talk a little bit about some of the ingredients in the proof. I'll focus just on virtual Z2. Okay, so that our Z2 cross a finite group, trying to show that there's a subset of virtual Z2 that only tiles non-periodically. The thing is, to conduct counterexamples, so the problem is this tiling equation is too rigid. You want to somehow replace it with a more flexible system of equations that I mean, it's this delicate balance. You want enough equations that there is that you can force non-periodicity. Right? So you want to somehow only have non-trivial solutions. But if you put too many equations, then there's no solutions at all. So you want you want to fine-tune the equation you're solving to have sort of an interesting solution space. So one of the first things we do is that we replace the single tiling equation with a system of tiling equations using kind of a sandwich construction, which I'll talk about. And now instead of solving one tiling equation, you're solving a system. And this system actually gives you a kind of computer language, that each tiling equation can be as a constraint. And it's trying to say something about your tiling. And you can put them all together to create very interesting problems. And it turns out, after a lot of experimentation, the type of problem that you want to create a puzzle of some sort which can be solved, but only has non-periodic solutions. And it turned out that the correct puzzle to type of solve is what we call a Sudoku puzzle. And I'll show you why. And what we eventually did is that we constructed what we call a quadratic Sudoku. And it looks like the classical Sudoku problem, kind of. And it can be solved. Instead of solving on a square, you solve it on an infinite strip. But the only solutions are non-periodic. And you can use that to solve the original problem. So you can encode Sudoku into the tiling problem. I mean, this type of idea, the way you prove things are not decidable or otherwise difficult is that you try to encode some other problem that you already know to be difficult. And so the trick is to find the right problem to encode and also to get the right encoding. Okay, so let's talk about some of the ingredients. All right, so the problem is, the original problem is you want to find a single tile F such that you have a single equation F plus A equals the group, and you want to show that this equation has you want existence, you want that there are solutions, but you want that the solutions are bad, that they're not, that they're all non-periodic, that the solutions are kind of weird. So we will generalize the problem. So instead of having one tile to get one equation, we create m tiles, and instead of solving one equation, we solve a system of equations. We try to find sets A, which are simultaneous tiles for all the simultaneous tiling sets for all the tiles F1, F2, F3 separately. So a single set of shifts which tile F1, which are a tiling set for F1, a tiling set for F2, and so on up to Fm. And that's a system of equations for A, as opposed to a single equation, right? Just like having a system of linear equations versus a single linear equation. So this creates a larger class of equations for which we can hope to find one system that has existence of solutions, but all solutions are non-periodic. But it turns out that these problems are equivalent. It's like when you have a system of linear equations, using matrices, you can convert that into one single linear equation. And there's kind of a similar trick in tiling, that if you have a system of tiling equations, if you want a set A to tile a lot of tiles simultaneously, what you can do is that you can take all those tiles and layer them together into a sort of a sandwich. So a sandwich, you've got a slice of bread and a slice of cheese and so forth. And you can create a three-dimensional object out of two-dimensional slices. And as long as you're willing to increase the size of your tiling of your ambient group a little bit, you can turn a single, like m separate tiles into a single tile in higher dimensional space, maybe your original group cross a cyclic group, for instance. The single tiling problem for the sandwich, if you do it correctly, is equivalent to the simultaneous tiling problem for the slices. Okay, so this is my single AI-generated image. So I wanted to see if ChatGPT can illustrate this concept. So if you have, so each of the jigsaw piece puzzles represents one tile. And if you want to tile R2 multiple times by this, first by one type of jigsaw piece puzzle and then by another piece and so forth, but always using the same shifts, what you can do is that you can stack the tiles together to form a three-dimensional tile. And if you do it correctly, the only way that you can tile this stack or sandwich of 3D tiles in space is basically by finding a common partition, a common tiling of each of the slices. There is this, you have to make sure that you can't slide up and down and so forth, but there are some caveats to making this argument work. But that is the general idea. And so yeah, I explained this to GPT, and they actually give a possible image to illustrate the process. Okay, so the reason why this is useful is that so any individual tiling equation is a single constraint on your set A. And it turns out that there are, if you choose your tile correctly, individual tiles can give rather interesting constraints. So like if you want your tiling set to be periodic in a certain direction or to have some sort of permutation structure in some direction, you can encode that as a tiling equation. And so you can create what we call a tiling language. We want to express a property of tiling sets A that is solvable, is satisfiable, has a solution, but for which the only solutions are non-periodic. Right? We want to describe a non-periodic set. Now, it is easy to describe non-periodic sets if you have access to all the mathematics. So, for example, the prime numbers are a non-periodic set. But I don't know how to describe primality as a tiling equation problem. But there are other things there are other properties of sets, subsets of a group that you can describe as tiling equations. And then now we have a tiling system. If I can combine them, so maybe each of them separately is not aperiodic. Each of them separately has a periodic solution, but maybe their intersection doesn't. So the idea is to sort of develop a very expressive tiling language that can express many, many properties about a set A that can be converted into tiling equations, and then combine them together into a very complex property of A that is still expressible as a tiling equation, and which only exists in non-periodic solutions. So you want to be able to have a language that's expressive enough to start describing non-periodic sets. Okay. So ideally, if you could get enough number theory expressed that you could define prime numbers, for example, then you're done, or square numbers or whatever. There's lots of examples of non-periodic sets. So it's so the question is, you want to put up sort of this library of useful properties of useful expressible properties that are expressible as tiling language, and hopefully maybe they're closed under various like Boolean operations and so forth. And so the philosophy we had was kind of like how if you want to program a complicated program, you first put up software libraries where you do basic operations, and then you just chain them together to form more and more complicated operations. So some examples of this. So there are arbitrary sets, like if you take a product set G cross H, that's a group. There are many, many sets, subsets of G cross H, but some of them are graphs. If you take a function from G to H, you can always graph, and a graph is a special type of set in G cross H. And the property of being a graph is something that you can express in tiling language. That if you have a subset of G cross H and you want it to be a graph, that's the same as saying that it's a tiling set for the vertical axis, the y-axis. That if you take a graph and you use it to shift the y-axis around, your set A tiles all the space if and only if your set A is a graph. This is a very fancy way of describing the vertical line test, which is what we teach to American high school students and undergraduates as to what a function is and what a graph is. So this is maybe this diagram will explain it. So here's G cross H. I think of G as discrete and H as continuous. So this set A is a graph of a function because it satisfies the vertical line test. Every vertical line intersects the graph exactly once, And that's the same as saying that if you take the y-axis, which is h, and you shift it by the different elements of A, that tiles the space. So the tilings of G equals H by H are in one-to-one correspondence with the graphs. Okay, so the property of being a graph of a function is a property of a language. A more complicated example of an expressible property is, now let's take the x-axis to be the integers and the y-axis to be a cyclic group, z mod nz. And now I say that I want my set to be a graph, and so that we already know how to encode. But a very special type of graph, a graph of a permutation. Like what I call a periodized permutation. So if you have a permutation of z mod nz to z mod nz, you can unfold the permutation and you can make it a periodic function from z to z mod nz. And so those functions, for example, if you take z mod 4z, the permutation that sends 1, 2, 3, 4 to 1, 4, 2, 3, say. That's a permutation, and you can unfold it and you get a sequence 1, 4, 2, 3, 1, 4, 2, 3, 1, 4, 2, 3. This is what I call a periodized permutation from z to z mod 4z. And the property of being periodic, this sort of periodic permutation in the horizontal direction is also expressible as a tiling equation. It's very similar to the previous example, but instead of using a vertical line segment as your tile, you use a horizontal line segment as your tile. So this is easiest to explain with a picture. So here is, so the x-axis, you think of the integers, y-axis is z mod 4z. This is the permutation, I think, 1, 3, 4, 2. So if you take 1, 3, 4, 2, and you repeat it periodically, 1, 3, 4, 2, 1, 3, 4, 2, the graph is this sequence of points like this. And if you take the horizontal line segment of length 4, 0, 1, 2, 3, and you shift 0, 1, 2, 3, this horizontal line segment by every point of this periodic permutation, you will cover all of z cross z mod 4z. And conversely, it's not hard to show that the only way you can tile z mod 4z, z cross z mod 4z by this horizontal line segment is by periodized permutations. So this tells you that the property of being a permutation up to some periodicity in a certain direction is, you can express it as a tiling length constraint by choosing the well-chosen tile. So you can keep doing this, and you can find more and more expressions that you can describe. So I said, you can encode the property of being a graph of a function, and so because of that, you can now start talking about functions, and you can try to encode properties of functions as tiling equations. So we saw, for example, being periodic in a certain direction, so being a periodized permutation in a direction, that is an expressive property. You can say that being periodic in a certain direction, this can be expressed as a tiling language. Being Boolean in the sense that it only takes 2 values, that you can express, there's a trick to express that as a tiling equation. If you have m Boolean functions, you can express Boolean constraints. Like you can say that you can start encoding satisfiability constraints, like f1 and f2 and f3 are not simultaneously equal to 1. That turns out you can encode with some asterisks as a tiling equation, and you can encode being in permutation. And you can start encoding various types of constraints that begin to look like the type of logical constraints you see in Sudoku. And so at some point we started experimenting with Sudoku type puzzles in the hope of searching for an aperiodic puzzle. So what is Sudoku? So you're presumably all familiar with classical Sudoku. There are many, many variants, but this is the most popular variant. So a Sudoku problem is that you have a 9 by 9 square, and you want to fill them with digits from 1 to 9. Often you are constrained that there's some initial conditions. Some of the entries are already given to you, and you need to complete to a complete Sudoku. And so a complete Sudoku is a way of assigning digits to every cell in this domain, which is a 9 by 9 square, such that every row is a permutation, 1 to 9, every column is a permutation, and every 3 by 3 block is a permutation. Okay, so that is the classical Sudoku. So we don't use exactly that Sudoku. That would be an extreme coincidence. So we invented this thing which we call quadratic Sudoku. We eventually realized that in order to get this delicate balance, to get a property that was solvable but only solvable non-periodically, it should be solved. Somehow the solution should be as close to being periodic as possible without being periodic, so almost periodic. And we had some other results that sort of suggested that was the right thing to look for. A good example of an almost periodic function comes from p-adic valuations. And so we eventually came up with the idea of what we call a p-adic Sudoku. So this is an example of a 4-adic Sudoku. So the solution space is not a 9 by 9 grid, it's I think a 16 by infinity strip. And you want to, so it's a strip, and you fill every single cell with a digit from 1 to 3. Okay, so the non-zero elements of Z1 QZ in general. And they have to satisfy certain properties. So the every row has to have a certain structure, and but also every diagonal. In fact, every line of integer slope, if you look at the numbers on that row, it's not quite a permutation. It's more like these periodized permutations, but actually these almost periodic permutations. So there are certain constraints that you can impose on all the rows and diagonals of this puzzle. And it turned out that there's a way to select different to create such a puzzle such that solutions exist, but the only solutions are non-periodic. To say one thing about the way you construct it is that so the every row and every diagonal has to look like this function here. So this is the p-adic last digit function. So if you take an integer and you represent a base q, and you look at the final digit of the final non-zero digit of your number base q, that function we call f sub q. So like if in base 4 your number is 3120, your function would assign the value 2, because 2 is the first non-zero digit. So basically, you divide by q until you're co-prime to q, or not divisible by q, and then your remainder mod q is this function. So this is a function that is almost periodic. So like if you're not divisible by 4, it's just 1, 2, 3, and then something, 1, 2, 3, something, 1, 2, 3, something. So it's periodic outside of a coset of 4z, and then inside 4z, it is periodic outside of a coset of 4 squared z, and so forth. So it has this p-adic structure. It's almost periodic, but not actually periodic. And you basically want your Sudoku, to solve your Sudoku, it has to look like this almost periodic function in every direction, every direction of finite slope. And it turns out that if you enforce that, and then you have to enforce a very minor non-degeneracy condition, then you also have to have this, it implies also having this p-adic structure in the vertical direction, and that implies non-periodicity. And so you can create these non-periodic Sudoku puzzles, and using this tiling language we talked about, it's possible to express this in, convert this problem into a very complicated tiling equation, and this is how we disprove the periodic tiling conjecture. Maybe I'll just say one more ingredient. There's this very simple lemma from additive combinatorics that was motivating for us, and so this is a cute statement which maybe I would just say is one of the inputs. Well, a variant of this is one of the inputs. That if you have a two-dimensional function, two variables, and you know that on every horizontal line it's linear. So it's an affine function on every single, or if you like, if you differentiate it twice in the x direction, it's 0. And if on every diagonal line, if of slope 1, on every diagonal line it's also linear. Those two facts themselves are not enough to force global structure, but if you're linear on every horizontal line, linear on every upwards diagonal, and also linear on every downwards diagonal, then you actually must be a linear function overall. So once you have linearity in three independent directions, that's enough to force linearity overall. So that's a cute little exercise actually. It's basically if your function is differentiable, it's not know how. You're saying that the three different components of your Hessian matrix are 0, then the whole matrix is 0. But you can prove it combinatorially. And basically we use a discrete variant of this lemma to sort of, that's ultimately our main input. Okay, so I think I will stop there. Thank you very much. I'll skip over the slides.
Thank you very much, Terry, for the wonderful talk. Are there any questions? There are 2 mics for people to use.
Thank you for a wonderful talk. what do you think about, I guess, what may be a stronger form of the periodic tiling conjecture where there's no period and even lower rank than
That's a great question. We don't know. Our construction it just sort of barely disproves the periodic tiling conjecture. We do have some partial results that suggest that, that, for example, we have a result that any tiling of a single tile in Z2 is what we call weakly periodic, that you can decompose into finitely many pieces, each of which is periodic in different direction. But it's possible to have a tile, especially a disconnected tile, in which some portion of tiling tiles is periodic in one direction, some is tiling in another. Yeah, we don't know. If we answer this question, we could maybe start attacking the Z3 question. So yeah, this is a good question. We don't know, basically, is a short answer.
Yeah. Have you formalized any of this work in Lean?
No. With Lean, it takes about roughly 10 times as long to formalize in Lean as to write papers. So currently, I'm never going to formalize more than 1/10 of my papers. I think I think right now basically I think you only want to formalize if you want to learn how to use Lean. I think so. My first formalization project was like that. Or if your theorem somehow it's very important to at least some people that there's confirmation that's correct. Or if the result somehow has potentially lots of applications. I'm hoping that this factor of 10 goes down in the next few years. And then, so in many cases, the logical strategy is to wait a little bit. And then I might go back and formalize some other older results of mine.
If I've understood correctly, tiling with one attached polygon, it can be represented by a system of, or set of linear equations. And each linear equation has a counterpart on the same polygon. Is that what creates tiling?
I guess you could think of it that way.
Because if it's symmetrical, there is half as many linear equations that can mirror.
Yeah. The equations are sort of linear in a way that's not easily usable. I mean, it's like if you take a convolution form, like 1 sub a convol 1 sub f equals 1, convolution is linear or bilinear. But you have this constraint that the two functions are indicator functions.
Right.
And so that makes linearity difficult to use. And so you can rephrase tiling equations as a system of some equations that are linear and then some things that are additional constraints that are nonlinear. You want multiplicity to equal 1 and so forth. It's like you can relax, there are linear relaxations of the problem. And those are sometimes useful. You can't transform it into pure linear algebra. Not exactly, but yes, you can certainly use linear algebra.
Could we not then just replace linear with just an equation that has a counterpart on the same polygon, correct?
I don't know. There's a lot of subtleties. I wouldn't, you can try. I think if you actually write it out carefully, there might actually be some issues, but I'm not sure.
Maybe one more question?
How expressive is this tiling language? Like how many things can you express? Can you express kind of like all of logic?
No.
Quite. Okay.
So, okay. So first of all, if you have two tiles instead of one tile, you can encode arbitrary Turing machines. And so we can prove undecidability there. Rachel will talk this afternoon. We also have a construction which actually, with a slight caveat, this tiling language actually also encodes arbitrary Turing machines. The catch is that we don't tile all the space. We tile a periodic subset of space rather than all the space. So we believe that it is ultimately rich enough to tile pretty much almost anything. I don't know if we can express arbitrary first-order logic statements of arithmetic, but we can get as far as Turing machines, which is enough for undecidability.
So tilings are related to non-commutative spaces. Is there analogy for non-decidability on the non-commutative side?
I don't know. I mean, people certainly study non-abelian tilings, tilings of non-abelian groups. And, tiling by rotation, just even rotation and multiplication, that is an action by a non-abelian group. But maybe by non-commutative, you mean something else. You mean more like quantum type?
Right.
Yeah, that I don't know if there's any literature on sort of quantum type tiling. I mean, I'd imagine it's worse. I mean, in that there would be many more counterexamples, but I don't know any literature on that.
We will be available for another 10 or 15 minutes in room 204 if people have other questions. Let's thank Terry again.